Good morning. Are you able to see the presentation?
Yes.
Yes, sir.
Yeah. In the last lecture, we are discussing about various policies and mechanism for efficient resource management. So we have looked at what are the different policies which we need to consider for the, as I mentioned, efficient management. So we need to consider uh, uh, both the client perspective as well as a provider perspective, right? So that means from the client perspective or the cloud customer perspective, you have to see that okay, you are providing the service with the best performance, and at the same time, you have to make sure that the cloud provider will have enough profit, right? So where he can get the profit in the sense where that cost cutting can be done, right? So maybe one is maybe with respect to the power consumption. So we already discussed, right? So how the power consumption can be reduced, and at the same time maybe you provide a best effort service and all. We have looked at some different mechanism, right? So one is maybe in general that control theory based we have discussed, right? Where in the case of control theory, where each application or the host will be having maybe small maybe component which is called as a sensor, right? So which periodically send the parameter related to that particular server uh, to the control unit, right? And so based on that particular parameter, it decides, right? So whether it should allocate more resource or not, that is done by with the help of another component called as the actuators, where actuator and sensor components both reside in the server. And we also looked at other one more mechanism, right, where you have maybe different independent manager, right? So one is a performance manager and power manager, and how they coordinate with each other so that so both are benefited in the sense that the cloud customer also get benefited and the provider also get benefited. Okay, so in the literature you can see maybe a lot of maybe, so these are the policies and mechanism maybe that is explained given in this in the book. Maybe in the literature survey you can give you can see hundreds of paper on different mechanism for the resource management. Okay, after that we looked at scheduling algorithm, right? So that means how you can scheduling, you can think it at different levels. Okay, so one is maybe how you can, as I mentioned, when you request for a virtual machine, right? So where exactly that virtual machine will be created, right? So there are thousands of servers, right? So how you can schedule that virtual machine in one of the server. That is one level. And at the higher level, if you think if you are considering submitting any applications or job, so where exactly that will be executed? All right. So in which virtual machine it will be executed? And in the cloud there may be the different class of applications. Okay, so this class of application may be mainly categorized as best effort policies and soft requirement and uh, hard real-time requirements. Okay, so we have seen one example, right? So best effort policies in the sense normally the batch applications, okay, where they will not impose any constraints saying that it should be completed in within particular time and all, right? So that is the best effort policies. Then after that, uh, so there are some kind of application soft requirement. Okay, so they may not they will not ask for a hard requirement, right? It should be completed in this much time and this and the performance is of this much only. Okay, there is some soft requirement, and hard real requirement. It says that it should be completed in this period only, and it should have this quality only. Okay, so now maybe in the cloud you may host the different types of application which may belongs to any one of these categories. And one of the important things to be considered in scheduling is that we have to make sure that the scheduling it should be fair. The scheduling it should be fair. So when I talk about this fair, right? So maybe there are different definitions and implementation of this fair scheduling algorithms. Okay, maybe we'll see maybe one or two, right? How exactly that fair scheduling algorithm works. First, let us look at one of the simple, uh, maybe how that fairness is evaluated. That is max-min fairness criterion. So that is called as the max-min fairness criterion. Okay, so what exactly it talks about this max-min fairness criterion? So consider a resource with the uh, a, a bandwidth B shared among the n users who have equal rights. The user requests an amount of BI and receives capital BI. Okay, so one more important thing is that see the some of the paper which we have discussed. Okay, maybe the algorithm, whatever it may be. So this algorithm, see these algorithms are based on some of the research paper, right? And these papers were written maybe before maybe 2000 only, before 2000, and actually that algorithm was designed for the network. So it was designed for the network, but the same idea can be incorporated uh, for cloud scheduling also. Okay, so because of that, you see the you have to map that concept into how we can map uh, this algorithm into the cloud environment. Okay, so now with respect to this max-min fairness criterion. Okay, so now let us say that consider a resource with the bandwidth B. Okay, so the resource which is having a bandwidth of B shared among n users. Okay, so the resource with the bandwidth of B and shared among n users. Okay, who have equal rights. Okay, so then each user uh, request an amount of BI. Now let's say that they have the equal right, but they have requested the requested amount is BI. Okay, so that is BI. The smaller BI is which they have requested. Okay, and receives a BI. So that is the capital BI. So that what they have received. Okay, so smaller one is which they have requested, and capital BI refers to what they have received. Okay, so according to the max-min criterion, so the following condition must be satisfied by the fair allocation. Okay, so what exactly this talks about? The first one, the amount received by any user is not larger than amount requested. Okay, so the amount received by any user is not larger than the amount uh, requested. Okay, as I mentioned in the previous slide, so where a smaller small letter BI, okay, which represents requested, and what they have received is a capital BI. And according to this, what they say is that so the received should be always less than the received should be always less than or equal to the requested. Okay, so the received is always less than or equal to whatever you have requested. And if the minimum allocation of any user B is B min and no allocation satisfying the C1 has higher B min than the current allocation. Okay, so so whatever the resources requested by each individual user, you have to allocate only that much. Okay, that much or lesser, but not more than that. So when you remove the user receiving a minimum allocation, so that is B min, then reduce the total amount of resource available from B to B minus B min, and the same process will be repeated. Here we'll see one example for this max min fair allocation. Yes, yes, compute the max min fair allocation for a set of four resources of four sources. Okay, so the 4 sources which request for the request for resource demand is something like this. They have requested for 2, 2.6, 4 and 5. Okay, so the question is maybe so there are requests from 4 users or 4 sources. Okay, so what is the request? The request is 2, 2.4, 4 and 5. But what is the resource capacity is available? The resource capacity is available is 10. Okay, so the available is 10 and that is requested by the 4 sources. And the request is a 2, 2.6, 4 and 5. Okay, then how exactly it will be allocated using max min fair allocation? Okay, so now as I mentioned, so there are 4 sources or 4 users, right? So the capacity is 10. Okay, first is it is something like this. You just equally distribute. So when you equally distribute 10 among 4 users, so each user will get 2.5. Right? So that now let's say that the 4 users or 4 sources, I will take it as A, B, C, D. Okay, now all A, B, C, D will get 2.5, 2.5, 2.5, 2.5. Okay, so next you look at the first user. The first user has requested only for 2, but he is getting 2.5. He is getting 2.5. But according to Maxmin, what it says? According to the Maxmin, it says that uh, uh, whatever it received, it should be less than or equal to the requested. Now it is for A, it is a 2.5, but what he has requested is only 2. So that means zero point 0.5 he will get extra, right? Zero point 0.5 he will get extra. So because of that, you should not allocate to 2.5. You allocate only 2. You allocate only 2. Then what is extra is a zero point 0.5, right? So zero point 0.5 is extra. Then you divide that among other 3. Okay, so okay, so then each one will get how much? So when you divide this zero point 0.5, so zero point 0.5 you divide and whatever the fraction, you just add it to the remaining 3. All right. So once again, when you look at for the second user he has requested 2.5. Okay, so now he will get more, that is 2.5 plus a point uh, 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 so when you divide this zero point 0.5 by 3, okay, so he will get extra, right? So then extra also you just remove, and then finally you distribute that to other. Okay, then finally what they will get is that yes, A will get to 2. So A has requested only 2 and he will get 2 only. And similarly B has requested 2.6 and he will get to 2.6 only. And user 3 and 4, okay, user 3 and 4 they'll be getting 2.7 each. So totally when you add this, it becomes 10. Okay, so the process is simple, right? So according to the max min, how it will be allocated, all right? So the resource allocated, it should be always less than or equal to what they have requested. Even though when you equally distribute, if they get more, right, you should not allocate more. Whatever they have requested, only that much you need to allocate. Okay, so the same example is given in here also, the pictorial representation. It is same thing only, maybe for better understanding. I think. Yeah, 2.645. Okay, it is the same example only. All right, where you can see that uh, maybe available bandwidth is of 10 Mbps. Okay, you can think this of anything. Okay, now here we are talking with respect to the bandwidth, or you can consider it maybe of resource also. Okay, so now what is requested? Requested is first user is requesting for yes 2, and the second one is 2.6, then 4 and 5. Okay, so now when you equally distribute, all right, so equally distribute. Uh, so let me write this. So that is a 2, 2.6, 4 and 5. Okay, so when you equally distribute, so each one will get actually 2.5. Each one will get 2.5. But for first flow or the first user, if you allocate 2.5, that will be over assignment. All right. So what is the residual is zero point 0.5. So what is the residual is 0.5. That zero point 0.5 you just distribute. 0.5 you just divide by 3. 0.5 divided by 3. So that becomes 0.1, 0.16. All right. So then that 0.16 you just add it to other three users. All right, so that is uh, uh, so now what you can see here for the second flow 2.5, and you are not adding 0.166 because for flow 2 you required only 2.6, right? So initially we already allocated 2.5, and if you add once again 1.6, it will be more. So 0.1 is sufficient. So because of that, you will see that 2.5 plus 0.1. Okay, now what is excess is the remaining is 0.066. All right, the 0.066, and this you divide by 2 with the last 2 and you allocate. So that is 0.066 by 2. Then you will get 0.03. So then once again you allocate this 0.3333. So you will get 2.7, 2.7. Okay, so that means the first user, okay, the first user will get the resource 2 only, and the second user what he has requested is a 2.6, and he will get 2.6 only, and other two users are requested 4 and 5, but available resource is less, and according to min max they are getting uh, they are getting 2.7, 2.7. Okay, it is something like this. Now let's say that you have uh, maybe so 10, you can think it 10 you can think as maybe 10 rupees, or you can think it as maybe 10 rupees. Okay, and there are four users. Okay, they requested for money. Okay, so one need 2 rupees, and other person is 2.6, and other is 4 and 5. Okay, so now how do you distribute 10 rupees for users? Okay, now the requested is first user has requested 2 rupees, and second one 2.6, and other is 4 and 5. Okay, then how you can allocate? Suppose equally share, each one will get to 2.5 rupees, right? Uh, but user one has requested only 2 rupees, so no need to give 2.5 rupees. So you just give only 2 rupees only, then 50 paisa is remaining, right? So that 50 paisa you can distribute among other three. All right, so then that 50 paisa divide by 3, and if you allocate that fraction to second user, then second user also will get more than 2.6 rupees. Then once again excess you just distribute to other two users, so 4 and 5. Okay, so that is about uh, uh, yes, max min fair allocation. Okay, so using the max min fair allocation, how you can allocate the resource. Similarly, there will be one more variation. So that is with the weighted max min. Okay, so that means each user is assigned weightage. All right, so along with the resource request, so there will be weightage. So you need to consider weight also. Okay, so while allocating the resource, you need to consider the weight also. Maybe in the same site, you will see one more example. One more example is given. Okay, yes, you can see here. Okay, so now the same example. Okay, so the resource you can think it as maybe 10. Okay, and requested is the user one requested is a 3, and 2 is also 3, and 4 and 5. Okay, then here the weight is mentioned, right? So weight for user one or user one, the weight is 1, and user two is weight is 2, and user 3 is weight is 1, and 1 and 1, user 3 and 4. Okay, now what do you do here? Yes, now what is yes, you have the total resource available is 10, all right, and the total weight is yes 3 plus 1 2 plus 1 3 3 4 5, so 10 mbps by 5. So that means fair share in the sense each user or according to the weight, so one weight in the sense 2 mbps. Okay, now for the first flow the weight is 1, so weight is 1 in the sense he will get 2 mbps. Okay, so he will get uh, 2 mbps, and for this second user weight is 2, so that is 2 times of that. So 2 times in the sense he will get 4 mbps, and other two users, that is user 3 and 4, they will get 2 mbps and 2 mbps. Okay, so now you look at here. So each user will get, the first user will get to 2 mbps, and second user will get 4 mbps, and the third will get to 2 and 2. Now what is requested here? User 1 has requested 3 and he is getting 2. Okay, so that is fine. And the second one, user 2 has requested 3. All right, 3, but he is getting more. So he is getting more, that is 4 mbps. So that is 1 mbps is extra. So 1 mbps is extra. So then once again you divide this 1 mbps, right? So 1 mbps, how you are dividing? So that should be shared among other three users, right? So what are the other three users? 1 3 and 4. So 1 3 and 4, what are the total weight? 1 1 1, right? So you divide it by 3. So 1 mbps by 3. So that means 0.333 you get. Then once again you equally distribute that 0.33 among all the three users, all other three users. That is 2 plus 0.33, and similarly user 3 and 4. So that is 0.33, 0.33. Okay. So that is this is a final allocation. So that is a 2.33, 2.3, 2.3. So when you add all this thing, all this, you will get yes 10. Okay, so here only thing is that you need to consider the weight. So you need to consider the weight. So right. So based on the weight, you need to allocate first. Then after that, if it is exceeds, if it is more than what they have requested, then that has to be distributed among other users. So that is a weighted max min. And the first one is so without the simple max min allocation. Okay, now this is some other example, so which illustrate the same thing, right? So the compute max min fair allocation for a set of four sources with the 4, 2, 10, and 4 with the weight 2.5, 4, uh, 0.5, and 1. Okay, so when the total resource capacity is 16, total resource capacity is 16. So this also once again same procedure. Maybe since here there is a fraction, right? So maybe 2.5, 0.5, and then either you can normalize it, and without a normalize also you can do that. Okay, so let me write the same thing here, right? So the requested resource is a 4 to 10 and 4. Okay, and what is the weightage given? 2.5, 4.5, and 1, and the total capacity is 16. Yeah, can anyone tell me, so when you follow the same procedure? So here the total weightage is 2.5 plus 0.53, 3, 4, 7, 7, 1, 8. So 8, so 16 by 8, 16 by 8 in the sense of 2. 2. So initially how much in the first iteration, how much they will get according to the weight? First user will get 2.5 weights. According to weight, how much they will get? According to the demand we allocate later, and according to the weight, how much they will get? So now let's say that the 4 users, let us name it as A, B, C, D. Right? The request is 4 to 10 and 4. And with the weight 2.5, 4.5 and 1 according to the weight. So the total availability is 16.
Four, sir.
Sorry,
I think four.
first user.
Sir, like there are four people. I mean four, right? So
Yeah, 4 people.
16
Yeah.
divided by four.
Okay. No, here we are talking about weighted max min. According to the weight you have to allocate. It is not equal distribution. So the total resource capacity is 16. Now you have to distribute based on this weight 2.5, 4, 0.5 and 1. How you can distribute?
Excuse me, sir.
Yeah.
I think it is 5, 8, 1, and 2.
Yes, 5, 8, 1 and 2. Yes, fine. Okay, then you just look at the demand. Okay, so now what is the demand? 4 to 10 and 4. Okay, now if you directly allocate according to the weight, the first user will get one extra, right? So that one extra you have to distribute among the 3. See, according to the weight, they'll get 5, 8, 1, 2. But what is requested is 4, 10, 4. So you have to allocate maximum whatever they have requested, not more than that. So first user has requested 4, but according to this, the weightage, they will get 5. So one extra they will get, right? So that one extra you have to distribute among the 3. So then what they will get in the next iteration, maybe step by step. One, when you distribute 8.4, 8.3, 1.3 and 2.3, right? Okay, then what is the next iteration? Second iteration, the second user, how much he is getting? What he has requested is a 2. Now he is getting
Sir is getting 8.
Yeah, he is getting 8. Then one extra which received, which A is received, that you will be distributing among all other 3, right? See, initially, so according to this weightage, so this is A, B, C, and D, and this is what they have requested. Request is 4 to 10 4. Okay, now maybe if you allocate according to their weight, okay, as I somebody said, they'll be getting 5, 5, 8, 1, and 2. Okay, but here the requested is 4, but here it is 5. So now what you can do is maybe you give only 4, and what is remaining is uh, uh, 0.3. Okay, so what is remaining is a 0.3, right? Sorry, 1. Okay, so 1 you can distribute among all uh, other 3 users. So according to the weight, okay, it is not 0.3. So what is the total weight here? So 1 you have to divide by uh, what is the total weight? So 4, 5. 4, 4, 5, 5.5. Okay, either you can take this, or maybe uh, I will normalize this. Okay, so normalize this in a sense. I'll take this as 5, 8, 1, 1 and 2. So that is 8 to 10, 11. So 1 by 11. So whatever the value you will get, all right. So that you distribute. So that is 4, 8 plus. So 1 by 11, right? And 1 plus 1 by 11, and 2 plus 1 by 11. Next, in the second iteration, now you see here, so whatever they are getting, it is more, what they have requested is 2, and but they are getting more, all right. And this once again you distribute among these 2 users. Okay, so whatever the extra, okay, so this total minus 2, total minus 2, so you will get 6 point something, and that 6 point something you distribute among these 3, these 2 according to the weight. Okay, then once again you just compare whether they're getting uh, uh, the resource which they get is less than or equal to what it is mentioned here. So that is 10 and 4. Yeah, the same thing is mentioned here. Yes, we started with the solution. The first normalize the weight. Okay, what they have done is, as I mentioned, right? So maybe 2.54, 0.5, and 1. All right, instead of calculating that fraction, they have normalized. All right, so this gives the weight as 5812. Okay, so this is over. Okay, then after that, yes, now that total, when you divide it by 16, okay, total divide it by 16, and in the first round each will get 5812. So that somebody is already told, right? So 5812. So this is still here it is fine. Okay, this we already seen, right? So in the first iteration 5812. Okay, then after that, so I'll retain only this one. Okay, then Yes, source 1 get 5 but only needs 4, right? So 1 unit is extra. Okay, as I mentioned, 1 unit is extra. So this is a 1 unit extra they are getting. Yes, and similarly, okay, here they have calculated, they have looked at uh, source 2 also at the same time. So source 2 they are getting 8, all right? Source 2 they are getting 8, but the requested is 2. So that means they have 6 extra. Okay, so they will be having a 6 extra, right? So that is what mentioned here. Then source 3 and 4 are backlog, so they have less resource. So, okay, so this is fine. Okay, then so this you already allocate 4. Okay, you already allocated 4. So initially they are getting 5 and you removed 1. And this second one also, all right? According to that weighted allocation, they are getting 5, but you removed 6. So then totally we have 6 plus 1, 7. 6 plus 1, 7 extra, right? Yes, now we have 7 unit of resource which has to be distributed among, yes, 3 and 4. So now you have 7 unit extra. So how you are getting 7 unit? 1 from the first and 6 from the second. Okay, now this has to be distributed to the last two users. Okay, now what is the weight for this last two user? 0.51 or 1 and 1 is to 2 ratio. Right, so when you divide this according to 1 is to 2 ratio, so what they will get? 7 by 7 divided by 2. What is the values they're getting? Yes, their weights are 1 and 2, and the smallest weight is 1. So there is no need to normalize the weight. Okay, so this is 1 is to. Okay, so finally what you are doing, what you are supposed to do is 7 is remaining, right? So 7 you have to distribute to the last two users. Okay, what is the weightage is given? It is 0.5 and 1. 0.5 and 1. In the sense, suppose one is getting 1 and other will get double of that. Okay, so that means one will get. You can mention this 7. One third of 7 will get will be given to uh, user 3. Okay, then 2/3 of 7 will be given to user 4. Okay, now how much they will get? What is the value? Yes, 1/3 of 7 and 2/3 of 7. So 7 by 3, and second one is 14 by 3. So that is 2.33, and the second user will get 12 and 4.66. So 4.66 is the second fourth user. Okay, roughly when you divide this 7 to the last two users, right? 2.33 plus 4.66. Okay, then that will be totally added to 7. Okay, now once again look at here. According to this, how much the last user will get? Last user will get how much the last user will get? See, the last user has requested for 4. He has requested for 4, but in the initial distribution, he is getting 2, and 2 plus 4.66. That is 6.66. So once again extra. So you have to allocate only 4. Then what is remaining at the end? That once again you have to allocate it to the user 3 only, because user 3 has requested 10. So user 3 has requested 10. So according to that, you have to distribute. Yes, that is what mentioned here, right? So first, what you do is yes, 7 into 2/3. All right. So 7 into 2/3. All right. So 7 into 2/3. That is for the last user. So in case of last user, how much he will get? So that is 2 plus this. That's what 6.66 he will get. But what he has requested is a 4. 4 he has requested. Then once again 2.66 extra. Then what is remaining? That extra, that is 2.66. So 2.66 once again you will be allocating to user 3 itself. Okay, so then final allocation will be, yes, so it will be something like this: 4 to 6 4, 4 to 6 4, right? So 4, so user A is requested 4, he is getting 4 only, and the user B is getting requested 2, and he also get to 2, and user 3 has requested 10, but he is getting 6, and user 4 has requested 4 only, and he is getting 4. So that is a weighted maximum. Okay, so next, yeah, the quality of service requirements that differ for a different class of cloud applications, and demands different scheduling policies. As I mentioned, that cloud can run a different. Yeah.
Sir, can you go to the previous slide once? Sir, so
Yeah.
In every iteration, we need to check for all the users, whichever has got extra, right? Not one
Yes.
by one.
Yes. Anything can be done. So then finally it yields to the same value only, right?
Yes, sir.
You just assign according to the weight. See, only two things you need to consider. You just assign according to the weight. Okay, in case if it is more than what they have requested, if it is more than they have requested, then extra thing once again you have to distribute to others according to the weight once again.
Okay, thank you, sir.
So here also, so this one is clear, right? First
Yes,
5812, where you had doubt.
Sir, I just had a doubt in the process that after the first round of allocation to each user,
Okay.
do we start, do we check with all the users all together, like which all of them, whichever has exceeded, we consider the residual for all the users, or we go one by one?
See, maybe if you are manually calculating, maybe you can consider two sources at a time. But if you are implementing, maybe if you are writing the program, then normally you have to consider step by step, right?
Yes, sir.
See, in this example, they have taken uh, source 1 and 2 together. You look at here, what they have requested is a 4 to 10 4. Okay, and according to the weight, it is 5812. All right, so source 1 has 1 extra, and source 2 has 2 extra. Source 2 has 6 extra. So 6 plus 1, 7 extra. Right, that 7 is they are distributing among last two. They have taken together in this example while illustrating. All right. But maybe when you write it algorithmically, maybe you will be doing step by step.
Okay, thank you, sir.
Excuse me, sir.
Yeah.
Sir, in the previous slide, why have we considered the source 4 first and then source 3?
Source.
Like we calculated for source 4 first and then we distributed it to source 3.
No. See here. So first you have this 5812. It is clear, right?
Yes, sir.
Okay. Then after that, so source 1 or source 1 will be 1 extra, right? And source 2 will be having 6 extra. Then total 7 extra is there, right? Is it clear?
Yes, sir. Yes, sir.
Then that has to be distributed among the last two users. And in the ratio of what is the ratio? 0.5 and 1, right? 0.5, 1, or maybe you can take in the ratio of 1:2. Alright, so when you divide this 7, okay, in this ratio, how much each will get? So you have what is remaining is the 7, and you have to distribute the 7 with the last two users. And what is the weight given? The weight is 0.5 and 1. 0.5 and 1 in the sense, suppose if you allocate maybe some x amount, and last user will get 2x. It is something like 1/3 and 2/3, right?
Yes, sir.
Yeah, 1/3 of 7 and 2/3 of 7, you will get nearly, so 1/3 of 7 is a 2.33. Is it correct? And 2/3 of 7 is a 4.66.
Yes, sir.
When you add that, you will get 7 only, right?
Yes, sir.
Okay. Now you just add uh, uh, so the extra to the source 3 and 4. So when you add, how much they will get? What was the initial allocation for source 3? According to the weight, how much they are getting? In the red line, it is
1 and 2. 1 and 2.
yeah, 1 and 2. So for 1 and 2, now you just add that extra allocated. So for user 3, what is extra? 2.33, right?
Yes,
And the
sir.
user 4 is 4.66.
Yes, sir.
So how much they'll get? It is 3.33 and 6.66. Correct?
Yes, sir. Correct.
Okay. So now you just look step by step only. Now you go to user 3. So user 3 has requested a 10 only, right? He has requested a 10 only, and now allocated is only 3.33, which is already less than that.
Yes, sir.
Is it clear? Okay, then you check the last one. User 4 has requested 4, but what they are getting now? 6.66. That is extra, right?
6.66. Yes, sir.
What is extra? 2.666 extra. Then extra you have to allocate it to only user 3 only.
Okay, sir. Yeah, got it.
Okay, so now this is about, as I mentioned, so there may be different types of applications will be running, and each may require a different quality of service requirement, right? It may be with respect to the deadline, or it may be the performance, or whatever it may be. So now when you look at this best effort, in the sense batch application and all, they do not require the quality of service guarantees. Right, when you run this batch application, right, they may not be having that much constraint saying that it should be completed within this deadline and all. Right, maybe some other class of applications, maybe soft real-time constraint, right? Maybe for the multimedia constraints also, multimedia application. Okay, they may be having more restrictions than maybe batch application, but maybe less than the dead than the hard time real constraint. Maybe some maybe mission critical applications and all. They may be having it like if it is to be done within this time, in a sense, it should be done in that time itself. Okay, deviation is not allowed. Maybe for a multimedia application, maybe small deviation will be allowed. And some of the algorithms, okay, some of the algorithm for best effort applications are maybe round robin, first come first serve, shortest job first, and so on. Right? So they may not. So so those best effort these algorithms, no. So they'll make sure that all application will be running, but it may not be with respect to maybe it may not be with respect to the, it may not consider the deadline also. And there are some other algorithms also. Some algorithm is mentioned, some algorithm given in the literature, like earliest deadline first and monotonic algorithms and all. Okay, so that is maybe used for real-time application. In the sense that will make sure that the real-time application will complete the task within the deadline. Okay, so next we look at maybe algorithms, some ideas. So that is maybe suitable for multimedia applications. So one is fair queuing and start time fair queuing. So where start time fair queuing is maybe it is a variation of this fair queuing itself. Okay, as I mentioned, whenever I said this fairness, right? So people will maybe having the different way of distributing uh, distribution of the resources. All right. For example, maybe let's say that maybe two thread is running, and let's say that it is using one resource. Okay, so one resource, and it is both the threads are given equal weightage. Okay, so both the threads are running, and both are consuming that resource. Now, in the case of fair queuing, what happens is now let's say that one thread is blocked. So one thread is blocked over a period of time. Okay, so when one thread is blocked, then the other thread can utilize all the resources which is allocated to this, as well as allocated for other thread, because that other thread is already blocked, right? So it is not consuming. So that can be used by uh, uh, the thread which is already running. But in the case of and once again that the thread which it is blocked, once again changed its state to ready state, then immediately fair queuing, what it does, it will reclaim, right? Reclaim, so that at the end both will get the equal share. Okay, so here they have given maybe some example. Okay, so why we have to go for this uh, fair queuing? Before that, they are giving some other examples, right? So maybe with respect to first come first serve, what is the problem with the first come first serve? Right? So maybe first come first serve will not consider the different class of application, right? So maybe first come first serve is something like this. There will be one queue, right? Maybe there may be different class of applications. All will be treated equally, right? Then other solution, right? So other solution will be something like this. Maybe you can have some priority queue, right? Priority queue, in the sense, maybe instead of one queue, you'll be having more than one queue. Okay, maybe each queue will is responsible for maybe one class of applications. All right, the first queue, okay, maybe that for maybe multimedia applications, and the second one for some other application, and so on. Then based on the priority, you are going to allocate. Okay, so that means if Q1, if the Q1 is given the highest priority, then whenever any jobs or task comes with the higher priority, you always picks from the highest priority. Now the problem is that whenever the highest priority queue is full, and always you pick from the highest priority queue only. In that case, that will affect the tasks of other queue also. All right. So instead of that, one more proposal is called as a fair queuing. It is just like, maybe let's say that uh, uh, maybe in a road, let's say that we are normal passengers, right? So maybe we are in when we are let's say that we are considering as a separate queue. Okay, and when maybe some MLAs comes and all, then maybe we have to wait until the MLA passes on that track. Okay, now the problem is that one day maybe all the MLAs are traveling in that same path. Then we have to stuck in that particular place itself, right? So that is what the problem with the priority. So now the fair queue, what it says that you will be having the number of queues, right? you will be having number of queues, but the picking of each task will be done in the round robin fashion. The picking of each task will be done in the round robin fashion. So now you have four flows: flow 1, 1, 2, 3, 4. Okay, so 1, 2, 3, 4. So you'll be picking one by one. Okay, now here also once again the problem is that okay, so maybe flow 1 will be having maybe job which may consume more bandwidth, which may consume more bandwidth. So in that case, the problem is that once again you are not equally distributing. You are not equally distributing. Or some other example is uh, uh, something like this. Now let's say that you go to a grocery shop, okay, and assume that there are two queues, okay, two okay, we will consider only the two queues. The queue1 is for the customer who require only few items, the grocery. Okay, if I want only one items, then I have to stand in one queue. Only one item I need. Okay, if anybody wants more items, if he wants to buy maybe more than 10 items, and he will be in another queue. Okay, so now so there are two queues. One queue is maybe a person who is buying only few items, one or two items, like that you can consider. And second queue is for the customer who is buying maybe more than 10 items at a time. Now once again you just look at the problem here, fair queuing, and it says that it will be fair, but actually it is not fair, right? So now when Q2 is served, one customer he is buying only one or two items. Then once again round robin fashion, when it goes to Q1, that customer is buying 10 item till that the customer in the Q2 has to wait. Now it is not that much fair, right? Because the customer one in the queue he is buying more items, right? Even though we are serving it in the round robin fashion, right? But it is uh, not that much fair, right? So now how you can make fair in the sense, once again, even though you require whether you require one item or two item, you serve one item at a time. From the flow one in the sense Q1, you want to he require 10 items. So first you give only one item, then you come to the second queue, and for that customer you serve one item, and then once again you go back to one and two, and the same thing you do that. Okay, that is what about the second one. That is bit by bit fair queuing. Bit by bit fair queuing. Now you cannot do like this. As I mentioned, you cannot give for one customer he needs a 10 item at a time, right? You cannot give one item to him and then you serve another customer, right? But you have to simulate that behavior. You have to simulate that behavior. Then how you can simulate that behavior in the sense? Now let's say that you have served the customer from flow 1. Okay, now he required 10 items. Now you served that. Then you go to second queue. You go to second queue, and second queue, now let's say that each customer require only two items. Then you serve for the 5 user from the second queue. You serve 5 user from the second queue. Then you once again go to Q1. In that way, you just you make sure that it will be fair. Okay, so now that is what mentioned here. So that is bit by bit round robin. So bit by bit round robin, which is a fair queuing only. Okay, now how you just look at here. So now here some notations are given. So FIA, which is equal to SIA plus PIA. Now what is SIA? Okay, as I mentioned here, there are multiple flows, right? So flow 1, flow 2, flow 3, flow 4. So in this notation, right, the superscript represents the flow. Superscript represents flow. So now SIA I of A, Si of A. Now what exactly that Si of A represents? Okay, so S represents the start time. Start time, okay, of packet I. Okay, the subscript represents a packet, and superscript represents a flow. Superscript represents a flow. So here A in the sense there may be more than one flow. Now let's say that there are 4 flow. Each flow is named by A, B, C, D, and so on. Okay. So now S represents the start time. Okay. Then P represents it is a packet length. P represents the packet length. Then what is the finish time? The finish time is nothing but S plus P. So S plus P will give the finish time. Start time plus packet length, which gives the finish time. Okay. Next, now let's say that one packet has already dispatched. Then what is the when the second packet will be dispatched from the same flow, same flow? So that is Si of A, which is equal to max of F I minus 1 A comma R Ti of A. So the max of that. Okay. Now here in the max where the second component actually represents, so that actually represents the arrival of the packet. Suppose if the second packet late arrived, okay, then the start time will be RTI of A only. It is something like this. Okay, so now let's say that in one flow, I will just take a numeric value only. So this is one packet. Okay, it has started at 1 and it has completed at 10. Okay, then second packet is arrived. So this is the second packet. Then second packet is the second packet is arrived at 10 only, you can consider, and it will complete at 2. Now this is what start time of this packet. Now here this packet I, when it will start, it is a max of okay, or you can consider like this. Okay, I will say that this is the first packet. Okay, and the second packet is arrived. Okay, it may be at 8 and 20. So when it will be processed? Now let's say that one is already started and it will complete at 10. It will complete at a time. Then when this one will start, even though if this has arrived earlier, and this will start at this one only, right? It has finished at 10. It has finished at 10. At 10 only it will be processed or dispatched. So now it will take this 10 max of this. Okay. Now this is referred to something like this. Now let's say that the first packet is 1 and 10. Okay, so now this first packet has a processed or whatever it may be. The second packet is not yet arrived. Okay, now let's say that it is arrived at 15 and it may require 25. Now when the second packet will be processed, second process not at finish time of this one. Okay, it is max of this. Now what exactly this refers to? This refers to arrival of this. Even though this has finished, the second one has arrived late. So then the second packet will start at this one 15. So that because of that only it is F I minus 1 A comma this. Yes, so the same thing is represented here. The same thing is represented here, right? So finish time. So the finish time is based on the, yes, suppose if previous one is finished already and the new packet is arrived later, then it will be, this will be the start time. Okay, otherwise another scenario is other scenarios, the other packet is already arrived, right? So then you have to wait till the previous packet is complete. And Okay, so next is start time fair queuing. Yes, a hierarchical CPU scheduler for multimedia operating systems was proposed by in the paper 142. Yes, so the start time fair queuing algorithm organize the consumers of the CPU bandwidth in the tree structures. Okay, where the root node is the processor and leaves of the trees are threads of each applications. Okay, now you just look at this diagram, so where you will get an idea. Okay, now let's say that the server, the root node is the server. Now let's say that in that server, two virtual machine is running. Okay, that is virtual machine 1 and virtual machine 2. Okay, and each virtual machine was given the weightage. Okay, now what is the weightage given? 1 and 3. So weightage is 1 and 3. So according to that weightage, it will use the CPU, the server resource. In the sense, now let's say that virtual machine 1 is executed for 1 second. It will execute for 1 second. Then immediately after that, the context switching will occur. Then virtual machine 2 will run for 3 seconds. Then once again the context switch will happen and it will execute for 1 second. Then 3. So based on the weightage, that context switch will occur. Now look at virtual machine 1. So each virtual machine can run more than one applications, right? Now let's say that that application which is running are 1 and 2. Application running are 1 and 2. Okay, that is A1 and 2. So within that, the weightage they have assigned. Now what is the weightage they have assigned? 3 and 1. Okay, that means A1 will be given the 3 weightage and A2 is given the weightage 1. Okay, so among that, once again, it will be equally distributed. All right, so the sharing is equally distributed according to the weightage, which is same as that of as I discussed in the previous example. Now look at A1 application. Each application might be having several thread. All right, that is what represented here. T11. So these are the 3 thread, and each will be given the different weightage. So according to the weightage only, so that will be allocated that much amount of the CPU share. Now how it will be scheduled, that is based on the start time. That is based on the start time fair queuing. Okay, so now the fraction of the processor bandwidth B allocated to the intermediate node I is Bi by B equal to Wi by summation of 1 to n Wj. So how much it is allocated? That is based on the Wi by Wi by total weight, right? For example, now let's say that in this previous example, now you just look at the root. Okay, the root, the VM1 is allocated weightage 1 and VM2 is allocated weightage 4. Now, how much fraction it will execute? So that is the total weight is 3 plus 1, 4. And its fraction of time is nothing but 1 by 4. And with respect to VM2, it is 3 by 4. That is what mentioned here. So 1 by 4 and 3 by 4. So according to the weight. Okay. Now here one more important thing is that yes, when virtual machine is not active, the bandwidth allocated to the other when a virtual machine is not active, its bandwidth is reallocated to other VM active at that time. Okay, now I said each virtual machine is given that much weightage, right? So now let's say that the particular virtual machine is blocked. So it is blocked. Then the resource allocated to that is also reallocated to VM2 since it is blocked. So that is what mentioned here. When virtual machine is not active, its bandwidth is reallocated to other VM. The same thing is applicable to application also. Whenever there are more application is running in that virtual machine, when one of the application of a virtual machine is not active, its allocation is transferred to the other applications. Its allocation is allocated to the other application, and the same thing is applicable to the thread also, at the thread level also. Okay, so now let's see one example of how that the start time fair queuing is running. some of the notation. So VA of t and VB of t, which actually represent the virtual time. It represents the virtual time of a two thread. Okay, there are two thread A and B. Okay, and V actually represent the virtual time of that particular thread, and where T represent the real time. Okay, so next Q is a time quantum. Q is a time quantum. Okay, so in which that particular thread runs. Now, how much time each thread will be allowed to execute? That is best. That is nothing but Q by WA and Q by WB. Total quanta by the weightage. Total quantum divided by the weightage. And here SIA represent the start time and F represent the finish time. Okay, so SI represent the start time and F represent the finish time. Okay, so now some notations. Please look at here. Okay, so R1 is that the threads are serviced in the order in which the virtual start time. According to the virtual start time only, the threads are serviced. Okay, and this R2 we'll see in the next lecture. And R3. So R3 is important. Now, what is the finish time? Okay, look at here. This is important. So what is the finish time? Finish time is equal to start time. So finish time equal to start time plus quanta by Wx. Okay. So now what is start time? It is a start time of the particular thread, and this is the total quantum given, and this is the weight of that thread. It is a weight of that thread. Then what is the finish time? Finish time equal to start time plus Q by Wx. Okay, so finish time is nothing but start time plus Q by Wx, where Q is a total time quantum. Now you see one example. Okay, so now let's say that start time. Now let's say that the start time is 0. Okay, one general example. Maybe this example is very lengthy. This we'll see in the next lecture. For the time being, now let's say that the start time is 0. Start time is 0, and the time quantum is 12. Start time is 0, and the time quantum is 12, and the weight assigned to that thread. Now let's say that it is 4. Okay, weight assigned to that particular thread. There are two threads are running, where weight assigned to thread B is 4. Then what is the finish time? Finish time is nothing but start time plus the total quanta divided by 4. Then what is the finish time? Finish time is 3. Okay, so here the start time is so here the start time is 0 and the total quantum given is 12, and the weight assigned is 3. So when the weight assigned is 3, then what is the finish time? Finish time equal to start time plus total quanta divided by 4. Okay, so that the thread will finish at 3. Okay, so rest we'll see in the next lecture. I think you have only 3 minutes of time. Okay, the quiz will start in 3 minutes. Yeah, any doubt with respect to computing the finish time? So finish time is computed as start time plus total time quantum divided by weightage. Okay, so your quiz will start in 2 minutes.